So I want to continue where we left off on Tuesday. And as I was just saying before our class began officially, I need to just discuss what I want to do, discuss where we are, and then I'll do an example, take you through an example. Okay. So what have we done so far? We described the conditions that must hold for stationarity, and then I went on and introduced. We discussed the three conditions for stationarity: mean, variance, and constant autocorrelations at same lags, right? One lag, doesn't matter where you begin. Two lags, doesn't matter where you begin. One lag autocorrelation must be the same of autocovariance. Lag two autocovariance must be the same no matter where you begin, and so on and so forth. And then we showed you, we explained what autocovariance was and autocorrelation was, okay? All right, so can you all see this page? This is from your textbook.
Yes.
Can you? Okay, good. So this is page, on this side here, it's page 45 of your textbook. And there it discusses autocorrelations. So this is how, how you calculate autocorrelation. So the autocorrelation is covariance divided by the variance, okay? And your book uses gamma, and gamma sub k. K means at the lag. So if you look at the covariance on top here, it says covariance between return to IBM at in 2000. I'm sorry, in 2020, that's time t, and return in 2018, that's 2020 minus 2. So the lag is 2, k is 2. If it's 2020 and 2019, it will be t equal 2020, then x sub 2020 minus 1, k1. So gamma k, meaning gamma at covariance, autocovariance at a specific lag. When the lag is 0, what is gamma? Variance, yes?
Yep, I think.
You can do better than think.
Yes.
Okay. What is covariance? Look, what is covariance? What is covariance x of t with x of t minus 0? That's x of t and x of t. That's variance. Okay, is that correct?
Yes.
Okay, so when k is 0, when the lag is 0, covariance is equal to variance. All right. And therefore, autocorrelation will be variance divided by variance will be plus 1. Okay? All right.
Yeah, got it.
Okay. And then we come in here and we break down this equation into its component. So this would be x, so the covariance, the one on top here, covariance would be return minus, so if you have a series, then you calculate the average of that series, that's x bar. And then you go back and subtract each one from x bar, and then the lagged one by x bar. We did all of this on Excel last week, remember?
Yeah.
Okay, good. So this is the equation for what we did. All right, so let me move on. So when you read this, don't freak out, okay? When you read this page and all these symbols, don't freak out. It's exactly what you and I did on Excel. And remember, what's his name again? Joseph Baghdadi, my man. Is Joseph here? Joseph Baghdadi. Oh my God, he logged onto Zoom earlier on. Joseph. Okay, so he logged on and he went away. Oh my God, these students. Okay, how is it? Oh, he's not there. He logged on like at 5:46. He logged on and maybe, all right, maybe he'll come back. All right, so this is an example. So in your book on page 46, I'm sorry, beginning on page 45 is an example where, it gives you a series of returns and it plots the returns. So these are the returns, okay? And then we calculate the autocorrelation at each lag. We did this last week. At lag 0, that's the variance. We calculated the variance, that's the autocorrelation at lag 0. And then at lag 1, we calculated the autocorrelation. Then we calculated the autocorrelation at lag 2. And then we plot autocorrelation against the lags, right? We did it last week. Is that correct? Lily, bail me out here.
Yes, it is. I just have honestly a quick question about
Okay.
this graph and like how I'm supposed to be reading it.
Which graph? Which one?
The graph B here. On to the second graph.
This one here.
Yes, exactly.
Okay.
So the autocorrelation function is always going to be like pretty high to start with because you're comparing it to like itself.
What do you mean? What do you mean?
It's always going to be 1. It's always going to be 1. The first.
No. Hold on. I know what you're saying, but you are not coming out right. So calm down. Talk
Please
to
correct
me.
me. I need clarification.
Yeah, talk to me. I'm having a soda with you at Baruch College Lounge. We're just talking. Calm down. So ask me the question. Use your own words. Okay, go ahead.
Okay, so maybe I was wording it correctly. Like at lag 0, the autocorrelation function here is 1. So
wait. At lag 0, the autocorrelation.
Yeah,
is
sorry,
1.
the autocorrelation is.
Okay, but what is the difference? Thank you, Lily, because I'm using you to explain this better. Okay, so don't worry about this. I know what you're saying. You know what you're saying.
No, I need the clarification because I'm,
Yes, I will give you the clarification, but I want to distinguish between autocorrelation and autocorrelation function. What is the function? Is the entire graph.
Oh, okay.
Okay, so the autocorrelation at lag 0 is 1, which is the variance. Is that right?
Yes, I think I misunderstood because on the axis it says ACF, so I was reading it as that unit is an autocorrelation function. So
no, the whole thing is autocorrelation from the graph.
Okay.
Okay, so there's autocorrelation at lag 0, that is 1. Is that right? That's what you told me?
Yes.
Okay, then autocorrelation at lag 1 is this number here. I don't know what it is. Maybe point, what is this number, Lily? 0.2? Okay, so 0.2. And then autocorrelation at lag 3 is small and so on. Yeah. You understand?
Yeah, so my question was, what are these dotted lines representing? Is that?
Okay, yes. So that's what I want to explain. Excellent, okay. Because I think that was the last thing I said last class, and then we ended class. Very good. Okay, so for now, let us forget the dashed lines up and down. Okay, let's just forget them for now. So these are the returns. We plot them, and then we go ahead and calculate the autocorrelations at different lags, just like we did in class on Excel last week. Everybody following me so far? And then we plot. You plot autocorrelations on the y-axis, and then plot lags on the x-axis, and then you don't need to join the point with a curve for now. Let's not join. So at lag 0, autocorrelation is always 1. So we plot it here. At lag 1 is this number 0.2. At lag 2 is this little number, and this little number at lag, and so on and so forth. At lag 8, it's negative. At lag 9, it's negative. At lag 11 is slightly positive. Now, hold on, let me go up. I think the autocorrelations are there up. They're given. Let me see. My picture is blocking my view, so let me move it. All right, so let me go up here. Oh no, I think it's further down. Right here. let's see if the numbers. Anyway, the R programs are there. Okay, okay. So we get the auto correlations at different lags here, up to lag 20, 21, 22, up to lag 24. 1, 2, 3, 4. Yes. So here we plot at each lag up to 24. We plot the autocorrelations. You see that? And we're not joining the points. We just plot the points here, and we connect them with the straight line down, and so on and so forth. Okay. Now, Lily.
Yes.
So suppose I want to check whether these autocorrelations are statistically not different from 0.
Okay.
You get it? So what I was trying to explain in a rather very awkward way last class, and I apologize to everybody because I was trying to relate it to the confidence interval that you studied in Echo 4000. So it was all over the place. So the point is this, everybody. The fact that autocorrelation at lag, let's say this one at lag 11. You see this one at lag 11 here? Everybody say it?
Mm-hmm. Yeah.
Okay. That's not 0. Yeah? It's positive but small. Is that correct?
Yeah.
Okay. But maybe for that sample we took, maybe the sample was, maybe it's really 0, because maybe that sample is a little bit not the very, very correct sample, or whatever. Maybe it's positive, but statistically it's 0. So that's why we have to build a confidence interval around, look this line. Look at this solid line. What is this solid line here? It's 0, right? This solid line is 0 at each lag. Is that correct? Are you with me?
Yes.
Okay. So any like lag 11 here, at lag 11 here, the autocorrelation is this height. It's not at 0, but it's this point. But statistically, it's not 0. Gosh, this drives me crazy. I want to, everybody, can you give me just 1 minute? I am going to stop recording, and I need to do something, and I'll come right back because I want to use it as an example, okay? Just everybody, please just wait for me. Is that okay?
Okay.
Okay. Everybody just give me 1 minute because I used to teach statistics. I'm going to stop recording now.
The recording has stopped.
Okay, I'll be right back in 1 minute, okay? I promise. 1 minute.
This meeting is being recorded.
Okay, everybody. Thank you. All right. Thank you, everybody. Now, I want to go back and forth with you guys. Okay, I'm going to show everyone 3 bottles of water. Okay, are you with me, everybody?
Yes.
So.
Okay, I'm going to show you 3 bottles of water. This is bottle number 1. Look at where the liquid is. Okay, this is bottle number 1. Do you see the level of the water? You see it, right?
Yeah.
Okay. This is bottle number 2. Do you see the level of the liquid?
Yes.
Does everybody see it?
Yes.
Okay. Good. This is bottle number 3. Do you see the level of the liquid?
Yes.
Okay. Which of the 3 bottles came from the factory as full?
The first 2?
No, this one, obviously, I already opened it and I drank it halfway. Are you with me? This one.
Second one.
Okay. No, the third one, I already drank it. Look at it. The third one is, okay, right. But which one is F-U-L-L-E-R, fuller? Is it this one?
Where's the one on the left?
For a
Is
little
Is it this one?
I can't see. The one on the left?
The first
Okay.
one you showed.
Okay, so
The
look.
one on your right.
Okay,
And-
so there are 2. Is it this one is more full?
bit. No.
Is it this one is more full?
Yes.
Okay. Everybody pay attention now, please. Everybody. If we define this height of water, this one, the one you guys say is fuller. If we define this quantity of water as absolutely the only definition of full, will this one satisfy us as a full bottle?
Yes.
No.
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 If we say this quantity of water in this bottle, the one you guys say is fuller, right? If we say this is our definition of full, strictly, you see that? Then this one cannot be full. We have to discard this, or we have to add more water to this. Are you with me?
Yes.
Yes. But Poland Springs shipped, they sold this too as full. Are you with me?
Yeah.
Yes.
Why? Because they
Let's not
gave
be satisfied with either.
an allowance. They gave a range for what they define as full. Are you with me so far?
Yes. Yeah.
Yes.
Okay. That is what we call confidence interval. You know, because, excuse me, guys, please listen carefully. If this was not water, but drug, but medicine for complicated cancer, then every drop of that cancer medication in here will be important. Are you with me?
Yes.
Yes.
In which case, if Poland Spring is the one producing this cancer medication, this one will not satisfy as full because it is a few drops below this one. Are you with me?
Yes.
Okay. So what we call full will depend on how important it is. If this was cancer medication, every drop counts. This bottle of water, this is the only full one. This one is not full because it's a few levels below. And that few levels below, if it were cancer medication, would be very important to curing of cancer. But this is just water. So Poland Spring has said that, you know, we can consider this full but this one is slightly below. We can also consider it full. But then we ask Poland Spring, hey, Poland Spring, how about this one? Would you consider it full, this one? Poland Spring will say no. Why? Can anybody tell me why?
Because it doesn't meet.
That level is not in the interval.
Because this level is outside of the range. Are you with me so far?
Yes.
Okay, thank you. Sorry. The same way, so let me go back now. The same way for autocorrelations. Guys, we say for white noise, what must our autocorrelation be at every lag? If we were to be very, very strict, what should our autocorrelation be at each lag? Tell me by voice.
It
Zero.
should be 0.
It should be 0. But what if we go through the lags and they are not 0, but they fall within an interval that we might consider 0? Is that acceptable? Yes.
How is that interval determined, though?
Aha, thank you. Now you ask me the critical question, my man. That sounds like who? Joseph?
No, that was me, James.
James, I'm sorry. Your voice is very unique, James. Okay, so exactly. Okay, hold on. So Poland Springs define the range that is important to them. We can define our range plus or minus 1 standard deviation, plus or minus 2 standard deviation, plus or minus 3 standard deviation. It is up to us to decide. Are you with me?
Yes.
Plus or minus 1 standard deviation is, that's like what, 67%, plus or minus 2 standard deviation, 95%, plus or minus 3 standard deviation, 99%. In fact, the wider the range, then the wider the range, then this water, even if it's here or here or here or here or here, will be considered full. Is that right? Are you with me? The wider the interval, then many bottles of water will be considered full. The smaller the interval, then quality control will get rid of some of the bottles. Are you with me so far?
Yes.
Okay, excellent. So James, the interval, the range will depend on us. So for example, I can tell you at 1% significance level, are these autocorrelation statistically 0? At 5%, so 1% significance level means 99% confidence. At 2%, at 5% significance level is let's create an interval at 95% confidence, and so on and so forth. Remember that from statistics, right?
Yes.
Okay, good. So exactly how do we, for autocorrelations, how do we build this interval, these dashed lines? Okay, which I will show you that in a minute. But
Okay.
Hmm?
I have one more question.
Okay.
Like in statistics, do we consider like outliers? Like, like if there are 1 or 2 that are, above what we consider, the range,
Okay,
can we discount them?
Okay, no, we're not discounting anything now because we are just testing the relationship between one return and another return at maybe 1 lag, 2 lags, 3 lags different, okay? So we're not discarding any. So we have a series of returns. And then we consider returns that are separated by 1 lag. We did it last week. Then we considered returns that are separated by 2 lags. We did everything last week on Excel. So we're not discarding anything. All the returns we use, okay? Now, somebody is chatting. Let me see. The outlier gets factored into the mean. Yes, okay, exactly. So we are using all the returns, just like you did on Excel last week. Everything we did on Excel last week is what I'm trying to explain here. We didn't throw away any number in that spreadsheet last week. All right. Now, everybody, please eyeball with me here. Let me make this a little bigger. Okay. A little bigger, even bigger. All right. If Lily can see this, I think everybody can. Lily, can you see this?
Yes, I can.
Okay, good. Now, according to this, is the autocorrelation at lag 0, is it statistically equal to 0 or statistically not equal to 0 at lag 0? It's not equal to 0. At lag 1, is it equal to 0 statistically?
No.
No.
At lag 2?
Yes.
Yes. At lag 3?
Yeah.
At lag 4?
Yeah.
At lag 5? Yeah. At lag 6? Yep. Ba, 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 ba. At lag
No.
12? No. At lag 14? Is it statistically equal to 0?
Yeah.
It's right on the boundary. Yes, it is statistically equal to 0. At lag 19?
Yes.
Is this autocorrelation positive or negative at lag 19? Is it positive or negative, this one at lag 19?
It's negative
Negative.
How do you know?
because it's below the line.
Fantastic. It is below the 0 line. You see that? Thank you. You see the 0 line, the dashed one, okay? And then this one, like 1 to 12 is not. So considering, suppose we are considering only 24 lags for this time series. And let's say this time series is returns on Facebook. Considering all the 24 lags, is that series of return, is it a white noise? No. Why not? Because of lags, which one? 1, 12, only those two. Because if those two were inside of the dashed lines, then we can say at 5%, at 95% confidence or at 5% level of significance, it is that this series is a white noise. If this one in lag 1 and lag 12, if they were between these two dashed lines, then we can say statistically, this series of returns is a white noise. Does everybody understand this?
Yes.
Okay.
Yes.
So how do we calculate the this dashed line? It's just like how you calculate confidence interval in statistics, plus or minus z times blah, 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 that equation. So I'll give it to you in a few minutes, okay? So when we calculate autocorrelations, at different lags, there are two tests we can perform. The first test is we test each one at lag 1. Is that equal to 0? We check whether it's within the interval. So this one statistically is not equal to 0 because it is beyond this interval. This is 0. We test them individually. Okay, and we use either the confidence interval or we use something called the t-test, just like you use the t-test in statistics. But then, does anybody remember that when you did Echo 4000, you also did something called the F-test? Does anybody remember?
Yes, I think so. I do.
What was the F-test? The F-test was you were testing whether together all the coefficients were equal to 0 or equal to 1 or equal to the null. So when we work with autocorrelations, we have two types of tests we can do. Number one is test each individual autocorrelations to see whether they are statistically equal to 0 or different from 0, in which case the null hypothesis is HO, the autocorrelation at that lag is equal to 0. The alternative HA, it is not equal to 0. It can be positive, it can be negative. So in other words, this is positive, lag 12 is positive, different from 0. Okay? All right. Another test is we test all of them together. Are they all joint together, jointly 0? We call that the joint test. So we use something we call the portmanteau. Portmanteau. Has anybody here visited London before? London, England? Has anybody? The answer better be yes. Okay, Nikhil, good. If you go to London, okay, if you want to leave your house in the United States to go to JFK or Newark to fly to London, what is the first thing you must do? You must pack your shirts, your shoes, your pants, your everything, pack them up and put them where? All together, put them where? What do you call that thing? In your suitcase, exactly. Or your luggage, is that right? In London, what do they call that suitcase? What do they call the suitcase? Portmanteau. Portmanteau. Okay, portmanteau. That's a very old word. I'm from Nigeria, so Nigeria was colonized by the British. So portmanteau is where you put everything, just like suitcase, your luggage or your suitcase. You put all your clothing, everything inside the suitcase, and then you pull it. You pull it, go check it in at the airport, or if it's small, you put it on you take it, inside the plane and put it up there. Are you with me so far? So when we do portmanteau test, we're testing jointly all the autocorrelations at all the lags together. It's like we pack them all together in a suitcase and test whether they are all, each of them is 0 and together they are all 0. If you test and together they are all 0, okay, and none of them is positive or negative statistically, then it's a white noise. Okay, now let me move on because of time. And after today, I'll have you read what I just discussed. And if you still have problems, you come back next week and ask me questions. Okay, so let me move on. Okay, everyone, just in the interest of time. Sorry about that. So how do we test jointly? So in your textbook on page, you see that portmanteau test, right? On page 47. Portmanteau test, you're testing them jointly. And I'll show you everything in a second. But let me move to page 46. All right, page 46. Okay, you see on page 46, correct? It says testing individual autocorrelations. So Lily, this can be confusing. They say ACF, so it's a function. So they believe you understand this, okay? But it should be testing individual autocorrelations, okay?
Yep, got
Okay,
it.
all right. So here, look, here, the null hypothesis is that the autocorrelation at lag 1 is 0. The alternative is autocorrelation at lag 1 is not equal to 0. It could be positive or negative, right? So this is what you call a two-sided test in statistics. autocorrelation at lag 2 equal to 0 versus alternative autocorrelation at lag 2 is not equal to 0. So we are testing each one. How do we test each one? Okay, you can do a t statistic using this formula, or you can just simply build a confidence interval. And I will show you my example in a minute, okay? Okay, guys, Lily and everybody, using our program, these are the autocorrelations at lag 0, at lag 1, at lag 2, up to, at lag 12, at lag 13. So R will give it to you. And again, maybe next Tuesday, since I didn't do it today, Thursday, next Tuesday, I will come in and do an example on R, okay, for everyone in class. Okay, everybody? All right. So we are testing each one, and then I'll show you in my example in a few minutes, the result. And then we can test them jointly. That's what we call portmanteau tests. It's like suitcase. Think of it as suitcase, okay? So we're testing all the autocorrelations at the same time, whether they are all 0 at the same time. And we use 2 types of test statistics, okay? The first one is given to us by a professor called, two professors called Professor Box and Professor Pierce. Box, B-O-X. I think he used to be in University of Minnesota, a very famous guy. Okay, Box, B-O-X, Professor George Box, I think. So he told us that if all the autocorrelations are jointly 0, that this is the test statistic you use. Remember, when you do a test in statistics, you can use the T or the Z, or you can use many types of statistics. To test this, you use this statistic. So this is given to us by 2 guys called Box Pierce. Okay, but there's another variation of this. This one is by another 2 professors called Professor Luang and Professor the same Box. So they use another test statistic given by T times T plus 2 and all that, because one of them is more powerful than the other given certain conditions. But this one, Luang Box, is the more popular one. So you calculate this thing here, but T is number of observations in your sample, T times T plus 2 times the sum of each autocorrelation at each lag squared divided by T minus that lag. We shall do an example and you see that. And then this number should come from a distribution we call not the normal distribution, not the T distribution, but because we are testing different things, the distribution it comes from is called chi-squared. Look at this. Is everybody looking at this? Chi, look, this thing chi-squared, this is how we spell it. Chi, C-H-I, chi-squared distribution. Because when you test, we are adding many, so we are adding many things. And each one has a distribution. So the sum of the distribution can be F, as you did in Echo 4000, or can be chi-squared, okay? All right. So if this number you calculate from the sample is larger than the number you pick up from the table, the critical value, if this number you calculate from the sample is larger than the critical value, you reject the null hypothesis that all the autocorrelations are jointly 0. If this number you calculate in the sample is smaller than the critical value, then you do not reject the null hypothesis. Guys, everything I'm explaining, at least you have the intuition from statistics and Echo 4000. Is that right? When you want to do hypothesis tests in Echo 4000, you take a sample, you measure something in the sample, you convert it to the Z of the sample, and then you go to the back of the book, you look up the critical Z, and then you compare. Do you remember that?
Yes.
Okay. And if it's outside the range, if your sample Z is bigger than your critical Z, you reject. If your sample Z is smaller than your critical Z, that means it lies within the allowable interval, then you do not reject. Okay, the same thing. So that's what this, so you can test each autocorrelation individually, or you can test them jointly, okay? In the interest of time, so what the example I'm going to do now is an example of what I just showed you from page 45 to 48 here, okay? So let me get out of here, and then let me discuss the example with you, everybody. No, you cannot see this. Let me share. Where is it? Okay. Okay. Lily, you see, I made the same mistake to ACF, right?
Yeah.
Yeah, but for me, this is the ACF. Okay, so the autocorrelation corresponding to lag 1, autocorrelation corresponding to lag 2, autocorrelation correspond. So if I plot this on a graph, this is the ACF, okay? That's why I wrote it, okay. All right, so what are we going to do here? Look, it says, suppose that you and I, researchers, we have calculated the first five autocorrelation coefficients at the first 5 lags using a series of returns, using a series of 100 returns, okay? Are you with me so far, everybody?
Yeah.
Okay. All right, so our observation is 100, 100, maybe 100 months or 100 days. So we have returns, and then we calculate autocorrelation at lag 1, just like we did last week. And then autocorrelation at lag 2. And those are the autocorrelations. Okay? Now, let us see, even though this is positive, this is negative, this is positive, negative, positive, none of them is exactly equal to 0. So what do? Let us test each of the individual autocorrelation coefficients for significance. In other words, let us test if they're equal to 0. And then let us also test all 5 of them jointly, portmanteau test, using the two tests, the box pairs, the first one I showed you, and the luang box test, LB test, okay? And let us test them at 95% confidence. Everybody following me?
Yes, sir.
Okay, awesome. Okay, everybody, please keep looking at this, because now I'm going to bring my solution and I'll take you step by step through the solution. You have it already on Blackboard, so bring it out and keep looking at it. Where the heck is, okay, this is it. All right. This stuff is very easy, everybody, okay? So please don't freak out. If you don't get it fully now, then read it at home, and if you still have a question, bring it in, okay? All right, so let's see. Sorry, my picture is getting in my way. I'm trying to move my picture away from, no. God damn it. All right, look, this is driving me crazy, but let's not worry about this. Okay. Okay, everybody. So this is the first thing we need to do is to test each one. And one quick way to test each one is I will build the confidence interval. Okay. All right. 1.96. Remember from statistics, 1.96 is 95% confidence, right? Plus or minus. We always say plus or minus 2 standard deviations, but it's really plus or minus 1.96 standard deviations. Yes? Okay. So this is plus or minus 2 standard deviations. So this is the autocorrelation functions. This is an approximation of their standard deviation, 1 over square root of the number of observations. Now, everybody just hold on. Let me go to your textbook. I think I saw it in your textbook, but let me just find it now. So I am on page 48. Let's go to page 47 or 46. It's somewhere. Let me just show you so that when you are reading the book, you will not. Okay, this is on page 47, example 2.1 continued. You see everybody? 2.1 continued. All right. So when you read it at home, it says here that using 1 over square root of t as the asymptotic standard error. In other words, in the limit, if you have a very large sample, we can use 1 over square root of t as a measure of the standard deviation of the autocorrelations. Okay, look, using 1 over square root of t as the asymptotic standard error or standard deviation of the sample correlation. Please read up to this point. It explains how it explains why we use 1 over square root of t as the approximation. But if I want to build a confidence interval, then I'll say plus or minus 1.96 times standard deviation, right? I want to build a confidence interval plus or minus 2 standard deviations interval. But really, for two-tailed tests, when we say plus or minus 2, that 2 is not really 2, it's 1.96. So I want to build an interval around 0. That interval should be, so if the average, if we're saying the average of the autocorrelations will be 0, on average, the autocorrelation should be 0. But if they are not 0, as long as they fall within an interval plus or minus 1.96 standard deviation, we can consider them 0. That's what we are doing, okay? So I'm going to use 1.96 times this standard deviation, okay? So everybody look at my solution. Look at my solution. Okay, so here I'm saying I want to create an interval plus or minus 1.96. Okay, so this is my interval. So plus or minus 1.96 times this sample standard deviation, and the standard deviation of autocorrelations is given by 1 divided by square root of t. Your textbook shows you why we make that approximation. Okay. What is my t in this example?
100.
100. So that interval will be plus or minus 1.96 times 1 over square root of 100, which is somebody is chatting. What are you saying in the chat? All right, let me move on. Dang it, I messed everything up. What did I just do? Sorry. No problem. Okay. Somebody says no problem. Okay. So plus or minus 1.96 times 1 over square root of 10 of 100. What is square root of 110? That's 1 divided by 10. So the confidence interval is 1.96 divided by 10, which is 0.0196 plus or minus. So the confidence interval is negative 0.196, positive 0.196. So in other words, this is the interval. So even if each autocorrelation is not 0, but they lie within this interval, okay? So guys, according to the graph I showed you in the textbook, we can look. Oh my God, what have I done? Sorry. We can draw a dashed line, you see? So I can draw, in this case, it's vertical. I'm sorry I put it vertical, but if you put this horizontal, then and draw the dashed line at positive and the dashed line at negative, it will be positive, negative, with 0 in the middle. You see, we just saw that picture in your textbook. Are you with me here?
Yeah.
So now everybody look at each of those autocorrelations and tell me which one falls within this interval or which one falls outside of that interval. Go ahead and eyeball them, everybody.
2 through 5.
Number 2, at lag 2, lag 3, lag 4, lag 5, each of them does what? Falls outside or falls within?
Falls within.
Okay, so if each one falls within, so your conclusion is that the autocorrelation at lag 2, even though it's negative, but it is really statistically equal to
0.
It is really statistically not different from 0.
Yes.
So would you reject the null hypothesis of 0 or not reject the null hypothesis of 0? Our null hypothesis is that each autocorrelation is 0. That's the null.
Well, the first lag.
So for the first one, what's your conclusion? Do you reject the null of 0 or?
Reject.
Huh?
I do not reject.
At lag 1?
Yes.
Does lag 1 fall outside of the range or inside the range?
Lag 1 is outside.
Huh?
Sorry, maybe someone else can take over, but
No, Lily, go ahead. You're doing fine.
Lag 1 is outside of that range.
So it's outside of that range. So my null hypothesis says anything within that range, we should consider it equal to 0. And the alternative says if it's not inside that range, then we should reject the null of 0. So for lag 1, that autocorrelation at lag 1, do you reject the null of 0 or do you not reject the null?
I think you do not reject, or you do reject. I honestly get confusing with the wording. I don't comprehend it, to be quite honest.
Okay, all right, okay. Does the autocorrelation at lag 1, does it fall inside or outside the range, Lily?
It is outside, but if it's outside, that means I am rejecting it because one of the lags falls outside of the range.
No. We're not thinking of all of them at once. We're thinking of each one separately.
So it rejected because it lies outside the range.
It rejected what?
That hypothesis.
And what is the hypothesis? What is the null hypothesis?
That it's equal to 0.
It's the null. It says HO, that autocorrelation at that specific lag is equal to 0. But because it falls outside of the interval, it doesn't fall inside the interval, it falls outside. So I'm going to reject that statement that says it's equal to 0. Yes?
Okay, so reject that statement. Okay.
So we are rejecting the null hypothesis for that lag 1. Yes?
Yes.
Okay. Lily, you're doing very well. Let's go to lag 3. Are you rejecting the null of 0 or are you accepting the null of 0?
I'm accepting the null of 0 because it is statistically 0.
Exactly. But in statistics, we don't say accept, right? We say we do not reject.
Do not reject. Do not reject.
Okay, excellent.
Okay, got it. Thank you.
Okay.
Appreciate the walkthrough.
Okay, so for each of them, we do not reject for lag 2, lag 3, lag 4, lag 5, and we reject for lag 1. Is that correct?
Yes.
Okay. By the way, everybody in this class, I'm dialoguing with Lily, but I could be dialoguing with any of you, okay? So if you don't get it, just stop me, okay, everybody? Is that a deal, my class? Tulemon, all of you? Somebody talk to me. Is that a deal? Okay, awesome. Now, so look, everybody, I can't even see my own solution. It is too tiny on my screen. So let me, gosh, this thing's driving me. This is, all right. So look, for the individual tests, HO autocorrelation at lag L, I just use 1 here, is 0. Okay? Okay? So autocorrelation at lag 1 is 0. We reject that because, like Lily said, it falls outside of 0. So we reject this null. So this is how you write. So if you want to test individually for this example, how many separate null hypotheses are you going to write? 5 of them. Are you with me, guys?
Yes.
But for the joint test, portmanteau, we're testing all of them together. We're saying the null HO autocorrelation. By the way, I should have a little hat here, okay? Meaning it's never mind. Let's not worry about that. I'll talk about that next week. So here I'm saying the autocorrelation at lag 1 is 0, lag 2 is 0, at the same time lag 3 is 0, same time lag 4 is 0, same time lag 5 is 0, and the alternative would be, so another way to write this is here, look, HO row 1, there's autocorrelation at lag 1 equal to autocorrelation at lag 2 equal to that at lag 3 equal to that at lag 4 equals to that, and equal to 0. So this is what we call a joint test, J-O-I-N-T. We're testing them jointly. That's why we use the word portmanteau. And the alternative is at least one of them is not 0. If one of them is not 0, then we cannot accept this null hypothesis. Are you with me so far, everybody? Lily, you're okay, good, very good. So even if one of them is not equal to 0, we cannot accept this null, then we have to reject the null, okay? All right, so we're going to use 2 tests. Okay, gosh, I just screwed up. You know, sometimes I question my sanity. All right, good. Now I bring it back to size. All right. So remember, to do portmanteau test, we can use 2 types of tests, box Pierce and luang box. I made a mistake with this star. In your textbook, the star belongs to the box Pierce, okay? And the Q without the star is the luang box. But I use the correct formula here. All right. So let us test the box Pierce. Q, do you want me to show you the formula again in the textbook, or do you believe me? So the Q equals T times the sum of each autocorrelation squared at each lag. So in other words, how many returns in our sample? 100, right? We are told. Yes, everybody?
Yeah.
Okay. So it's 100 times the sum of the square of each of the autocorrelations at each lag. So at lag 1, the autocorrelation is 0.207, so we square that. Plus, at lag 2, the autocorrelation is negative 0.013, we square that, up to lag 5, negative 0.022, I think, squared. Yes? Everybody following me?
Yep.
Okay. And if you multiply and add up everything and square everything and add up, the Q is 5.09. But the Q, the critical Q is distributed as a chi-squared. That critical is 11.1. So this number is less than this number, so you do not reject.
And you're getting that that critical value, and that's a 95% confidence. That's the 0.05.
Yes, so this 0.05 is 1 minus the confidence interval, which is what we call the significance level. Remember that?
Yes, yes.
Okay. So if you go to a table, remember, go to the back of the table go to the back of the statistics textbook, identify not the T, not the Z, not the F, but you identify the chi-square, this one, and you look it up. On top is 0.01, 0.02, 0.05, 0.10, and so on. So you identify 0.05, and then you look on the left-hand side, you identify T equals 100, the sample size, you will get this number, 11.1. You can also look it up in Excel these days. So because this number is less than this number, we do not reject the null. So we accept the null. And when we accept the null, we say they are jointly equal to 0. So you might argue that this is a white noise. Okay, but let's not introduce white noise now. Here we're just testing them jointly. The luang box is the same. We use Q equal to T times T plus 2 times all of the times. In this case, the autocorrelation at the lag squared divided by 100 minus that lag. So look at here. So the luang box is 100 times 100 plus 2, 102 times the autocorrelation at first lag squared minus 100 minus first lag, 1. Are everybody looking at that? Okay. Yeah. I made a mistake here. This negative should be inside the parentheses, okay? Sorry about that. So please correct that. So it should be negative 0.013 everything squared divided by 100 minus, because this is for lag 2 minus 2. And then you do it up to the 5th lag. This is the autocorrelation function at lag 5, negative 0.022. You square that and you divide it by number of observations minus that lag, 5. So you do the multiplication, the squaring, the division, the addition, everything, you get 5.26. It is still below this number, so you do not reject, you accept.
It's tricky, right?
No, it's not tricky. Briefly, I thought I made a mistake.
I heard you pause.
Yes, because I paused because I was thinking, did I write accept or do not accept? For
yes,
1 second, I thought I wrote do not accept, just for 1 second.
The wording is hard.
Yeah, so it is do not reject. Okay, I should write accept. If it's easier for you to handle, you should say accept.
Yes, makes sense.
Okay, and then please don't tell my statistics colleagues I said that. Okay, so we should accept the null here. We should accept the null here. We're using 2 different tests, statistics. This one is generally more popular, this one, the LB test, okay? But one final thing to say, next week, when we do an R example, right, Lily and everybody, we shall not be dealing with chi-squared because the R program will calculate for us the p-values in each case. Remember the p-values from statistics?
Yes.
Okay, so if we are testing this at 0.05 and it calculates the p-value corresponding to this, if it is less than this number, then we do not reject. I'm sorry, no. If it's less than this number, we reject. If it's bigger than this number, we do not reject. My fault.
Got it.
If it's less than this number, you reject the null. If it's bigger than this number, you do not reject the null. Okay? Okay, good. All right. So next class, next Tuesday, I will teach something. I will introduce you to the to another module, not white noise, but I will introduce you to another module. Either the I think I'll begin with the moving average. It doesn't matter. I will introduce you to one of them, and then I will do these tests using R. Okay, in class next week, next Tuesday. All right. So let me. Sorry, I think I kept you a few minutes beyond.
The recording has stopped.
All right. What time is it now? Oops, 7:11. Sorry. This class should end what time? 7:05, yes?
Professor, there is a question in chat. Like, how did you find 11.10?
Okay, how did I find
So,
it?
like,
If you have a statistics textbook, go to the back, identify the distribution called chi-square, right?
okay.
How did you all study Echo 4000? You just plug numbers in Excel?
Yes, sir.
No, we use the table.
Okay, you can go to the back of the table, or you can go, actually, you can go to Excel. If you go to Excel, go to functions, F, you know that little F in Excel, function, statistics, scroll down, look for chi-square, and then find it, okay? I'll do that on Tuesday for you. Don't worry about it, okay? I'll do it for everybody on Tuesday, okay? Who asked me this question?
I did, but it's like from like several students.
Okay. So let's review that on Tuesday. But actually in this class, you may not need to, because we are using R, you may not need to do the chi-square because R calculates for us the p-value. And the p-value is always the p-value is, the rule is if you calculate the p-value and the p-value you calculate is less than your alpha, then you reject the null. If your p-value is larger than your alpha, you do not reject the null. Okay? All right. Gosh, I'm exhausted. So who's asking me questions? So everybody have a nice weekend. Okay, I'll see you back on Tuesday. But if you have questions, you can wait and ask me. All right. Who's
Thank you,
asking?
Professor.
Good night. Okay, everybody leaving. Good night. But if you have a question, good. Thank you, Andrew. Good night.